Solution change the boiling point and the freezing point of liquids. So think about a solution with salt in it. We have sodium ions and chloride ions. Now there's an aqueous solution. Now in order for the water to become a gas, it has to escape. So it has to escape the pull of the other molecules. Remember, there are attractive forces between water molecules called hydrogen bonds. What happens here between the positive sodium and the negative end of the oxygen? Well, we have attractive forces there too, right? There's a partial negative on the oxygen, a partial positive on the hydrogen. And so that means we have some other attractive forces here between the negative ions and the positive ions of water. So as a result, there's additional attractive forces, and the ions are holding back the water. The water's attracted to these ions, and it makes it more difficult for the molecules to escape and become a gas. More energy is needed in order for them to escape and become held back by those attractive forces. So this is called boiling point elevation. The temperature at which a liquid boils, like water, because of the boiling point elevation. Now consider the example for freezing. So if we have a liquid that's going to become a solid, there's ice, for example, if we had water. Now, in order for it to become ice, it has to form a very structured pattern. It's called a crystalline structure. So we have this sort of honeycomb structure that forms with water. And so on. So we have this honeycomb structure that forms. Now, solute particles get in the way, and they sort of disrupt that pattern. So this makes it require lower temperature in order for it to freeze. And that's called freezing point depression. So let's apply this. Now, in order to find the temperature change for the boiling point, the change in temperature for boiling is found by multiplying the molality times the boiling point constant. And for water, the boiling point constant K sub B is 0.52 degrees Celsius per molar. Now, to find the change in temperature, delta stands for change in temperature for the freezing point, it's the molality times the freezing point constant. And for water, again, the freezing point constant K sub F is 1.86 degrees Celsius per molar. Now, why do we use that molality unit when we solve these problems? Why do we need molality? So that's what this unit is here, right? The M. Why do we need that? Well, molality is the number of particle moles divided by the kilograms of solvent. And that would be particle moles of solute. So molality is needed because it's a unit that takes into account the fact that some things dissociate. For instance, salt, NaCl, when it's put into a solution, it breaks up into Na plus and Cl minus ions. So you can start of salt that then becomes 2 particle moles. And the property in which the freezing point and the boiling point is dependent based on the number of particle moles there are. So that's why we need to use molality to solve these problems. So let's calculate the freezing or boiling point in these problems. Ethylene glycol, which is antifreeze, or the main component of antifreeze, a non-electrolyte is added to water in a radiator to give a solution containing 515 grams of ethylene glycol and 565 grams of water, the solvent. What is the boiling point elevation and the boiling point of the solution? The molar mass of ethylene glycol is 62.07 grams per mole. So antifreeze, interestingly enough, is both used to prevent freezing in a radiator as well as boiling. So on a cold day, the antifreeze prevents freezing. It lowers the freezing point, but engines can operate higher than the boiling point of water, and so the antifreeze prevents the coolant from boiling, because that wouldn't work very well. Cooling, steam has a low specific heat. It would not carry the heat away very well or have a good cooling property for the engine. So we need to have liquid water, of course, in the radiator. So we're going to figure out how much the temperature can be above the boiling point in a radiator given these parameters. So first we have the grams of the solute, the ethylene glycol. So let's write that down. We have 515 grams of solutes, and that is a non-electrolyte, it said. That's important to note. So right here it says it's a non-electrolyte. But what does that mean? Well, a non-electrolyte, we saw earlier, is something that does not dissociate. So when we put ethylene glycol into water, so here we have ethylene glycol, and you put it into water, you might have 1 mole before you put it in water, and you still have 1 mole, 1 particle mole of ethylene glycol. And that's in contrast with, of course, salt, which we saw, which would split into or dissociate into its ions. And so we would split into 2 particle moles, starting from 1 mole. So since it's a non-electrolyte, it does not dissociate, and that makes some things easier. We'll see in a moment. So then we also are given in the problem the amount of the solvent, and so we have 565 grams, and that's the solvent. So we want to know the boiling point elevation. So we want to know the temperature, T sub B, the temperature at which it boils. Now in order to find that, we're going to need the formula. The change in temperature of the boiling point is the molality times the boiling point constant, K sub B. So the change in temperature for the boiling point then, we need to find the molality first, and then we can multiply by the constant. K sub B, we know, is 0.52 degrees Celsius per molal. But the key here is we need to figure out what the molality is. So let's do that now. Now the first step is we need to figure out the number of particle moles. Since that's what goes into the equation for molality, we need the number of particle moles. So we need to think about the number of grams of solute and how that would dissociate into particle moles. So we just saw that since it's a non-electrolyte, however, non-electrolytes do not dissociate while electrolytes do. So since it's a non-electrolyte, the moles before are the moles after it's added to solution. So we could say that 1 mole of the solute is equal to 1 particle mole. So it's a 1-to-1 here, and so that makes things a little easier. We just need to convert the grams of solute to moles. So we have 515 grams of solute. The problem gave us the molar mass of ethylene glycol as 62.07 grams. 62.07 grams per mole of solute. And so based on this equality, for every 1 mole of solute, there's 1 particle mole. So there's no dissociation, so we have the same number of particle moles as we have moles of solute. So this gives us 8.29 particle moles. So now we need to use this with the molality equation. Molality is the number of particle moles divided by the kilograms of the solvent. Now the particle moles we just found right here. So we plug that in. The kilograms of the solvent, well, it gave us the grams of solvent, and we can convert that to kilograms. We would divide by 1,000, which would give us 0.565 kilograms. We plug those in, find the molality. So we have 8.29 particle moles divided by 0.565 grams. And so the molality then is 14.7 molar. Well, now we just need to take that and we need to plug it in to the equation. The change in temperature for the boiling point is the molality times the boiling point constant. So we just found the molality to be 15.7 molal. The boiling point constant is 0.52 degrees Celsius per molal. Molality cancels out. And so the change in temperature is 7.64 degrees Celsius. So that's part of our answer. The question wanted to know the boiling point elevation. So the boiling point elevation is 7.64. That's how much it changes. But the other part of the question said, what is the actual boiling point then? Well, that change is added to the boiling point of 100 degrees Celsius. So in order to know the actual temperature, it would be 100 degrees Celsius plus 7.64 degrees Celsius, or in other words, 107.64 degrees Celsius. And I'll consider that 100 to be exact. And so both of our answers, we know the change in temperature by adding the ethylene glycol, and we know the overall temperature as well for that problem. So let's now at the freezing point. Calculate the freezing point depression and the freezing point of 1.2 moles of NaCl in 1 kilogram of water. Alright, so this time, for this problem, we again list what we have, but we're on the other end of the spectrum. We're dealing with freezing point. So we have the amount of the solute given to us. We have 1.2 moles of solute. and that's NaCl. We also have the kilograms of the solvent, 1 kilogram of solvent. And so we want to know the freezing point and the freezing point depression. So we want to know the temperature freezing and also the change in temperature of freezing, or the depression. So we'll need the formula once again. The change in temperature of the freezing point is the molality times the freezing point constant. Now the freezing point constant for water is 1.86 degrees Celsius per molal. And so we have to, just like the last problem, figure out the molality, and then we can plug it in to the expression here. Now this time it's NaCl. Pay attention to what compound we have. NaCl, water, sodium chloride, dissociates into sodium ions, chloride ions. So since it dissociates into sodium and chloride, 1 mole of NaCl results in 2 particle moles after dissociation. So we need to take that into account when we figure out the number of particle moles. So to find the particle moles, we start with the number of moles of solute. We have 1.2 moles of NaCl. Now, based on this expression here, for every 1 mole of NaCl, there are 2 particle moles. So we'll need to multiply 1.2 times 2. We have 2 moles. Now we can plug this into the molality equation. Molality is the number of particle moles divided by the kilograms of the solvent, and this is of the solutes. Particle moles we found right here to be 2.4 divided by the kilograms of the solvent, which the problem said is 1 kilogram. So the molality then is 2.4 molal, and we can take that and plug it into the expression for the change in temperature of the freezing point is the molality times the freezing point constant. So we plug this number in for the molality, and the freezing point constant we wrote down up here. Plug those numbers in. 2.4 molal times the freezing point constant, 1.86 degrees Celsius per molal. And so the change in the temperature of the freezing point is 4.5 degrees Celsius. So there's part of our answer. The part right here, the change, we found that. So that's the freezing point depression. Now, the other part of the answer is to figure out what the actual temperature would be. Well, since the temperature of freezing in Celsius is 0 degrees Celsius, the freezing temperature then would be 0 degrees Celsius minus the change, 4.5 degrees Celsius, or in other words, the freezing point is just negative 4.5 degrees Celsius. And that is our freezing point depression and the temperature at which the solution would freeze.